Okay. Okay. So last class. Welcome to week 8 of NGS data analysis and applications. So last class we talked about structural variants, how to uncover them, and what are the different types of evidences that we look for while detecting structural variants. And also we touched upon RNA sequencing and technologies and alignment, RNA sequencing alignment technologies as well, how there are splice aware and splice unaware alignment tools. And today we are going to elaborate on RNA sequencing only. So basically, we'll look at different methods to pre-process the data on RNA-seq. Basically, statistical methods to process this data, and ultimately, like the whole pipeline for RNA sequencing is kind of getting the pre-processing the data and ultimately going for differential expression analysis, where you kind of look into the genes that are overly expressed in a particular conditions or underexpressed in a particular condition. And yeah, so let's get started. Okay. Okay. So first, let's talk about normalization and what do you mean by normalization in RNA sequencing. So gene expression is measured with RNA sequencing using the number of reads aligned to each gene under each biological condition. So basically what we do is we align the transcripts with some sort of tools like STAR or HiSat2, and we check what are the number of transcripts that are getting aligned to a particular gene. And the gene expression is quantified in that way. So the more the number of transcripts that are aligned, that means that gene is more expressed. The lesser it is aligned, the less number of transcripts that it is aligned into, it's the expression of the gene is low. But it's not as straightforward as that, because there are other confounding factors into play, such as the length of the gene or the depth of sequencing and other stuff as well. So we need to normalize those and along with the normalize those with respect to the number of reads or the number of transcripts that are getting aligned, so that we can have a better picture and understanding about which gene is getting expressed more and which gene is getting expressed less. So, a naive comparison of read counts for a given gene under different conditions is problematic for two reasons. First, the number of reads aligned to a given gene in a given sample is generally considered as a random variable, though non-random events such as inconsistent fragment amplification or poor amplification of certain sequences can impact final read count. And so, read count comparisons must take into account the variability of these random variables. Second, the total number of reads can vary across samples, as I was saying. So, large difference in the gene's read count between two different conditions may simply be the result of differential coverage rather than differential expression. As I was saying, like it may be possible one set of samples have been sequenced at a certain depth, another set of samples have been sequenced at a depth higher than that. So while we are comparing these different expression profiles of two RNA-seq data sets, we need to keep those things in mind, the confounding variables in mind. So it is the second problem that necessitates the normalization of read counts before differential expression analysis can be performed. So normalization is an essential step in RNA-seq analysis, in which the read count matrix is transformed to allow for meaningful comparison of counts across samples. So the read count matrix is a simple data frame. So basically on your column headers, you have all the samples, and on your row names, or actually your first column, you'll have all the genes. So it's a matrix format. So number of samples by number of genes, and at each point, at each element of the matrix tells you about what is the expression of that particular gene in that particular sample. So that is what count matrix means. That is the way of representing RNA sequencing dataset. And we apply these normalization methods on datasets like that, the count matrix datasets. With the advent of RNA sequencing technology, it was initially believed that normalization would not be necessary, but normalization have been found to be an indispensable for correct analysis of RNA-seq data. This one research found that normalization procedure used in differential expression pipeline had the largest impact on the results of the analysis, even more than the choice of the test statistic used in hypothesis testing for differential expression. So as you can understand, the importance of normalization is very high. So this is one such example why normalization is necessary. So on the left, you have basically you are measuring the expression of three genes under two conditions, this condition A and condition B. So an experiment is performed with conditions A and B to compare expression of three genes. This one, two, three are three genes, and these are to your A and B are your different conditions or different samples, different types of samples. So in the first figure, you see this gene 3 is twofold upregulated under condition B, while the other genes are not differentially expressed. Because 1, 2 are remaining the same, 3 is doubled up. Uh, yeah, gene 3 is twofold upregulated in condition B, while the other genes are not differentially expressed. The quantity of mRNA per cell is the same for genes 1 and 2, but is twice as high for gene 3 under condition B. So the proportion of mRNA that is inside the cell is basically it's like twice for the third gene and like it's one times for gene 1 and 2. Yeah. Uh, uh, yeah, so under these two conditions, so basically comparing condition A to condition B, your expression of gene 3 is twice as high compared to 1 and 2. Now, because of the change in the expression of gene 3, the shares of mRNA in the cell are different between these conditions. Under condition A, each gene gets one third, while under condition B, gene 3 gets half, while the other two gets one fourth. Okay. So if you see the reads aligned to each gene under each condition, so in condition A, all like kind of have the same depth of coverage, but in condition B, the amount of transcripts that are getting aligned to gene 3 is kind of twice than compared to 1 and 2. Differences in shares of mRNA are reflected in the shares of read. Each sample has the total number of reads, but the distribution is different between the conditions, matching the distribution of the mRNA in this condition. Right. So, in basically in this condition, you're measuring the amount of reads, and like you see, the number of reads aligned to the third gene is twice as compared to 1 and 2. So if there is no normalization performed, there are apparent differences in read counts for all three genes. So if you do not do normalization, you just check this thing, uh, and you don't do normalization, and you just check the amount of reads that are there. So what happens is there's apparent differences in read counts for all three genes. Total count normalization produces the exact same result as no normalization at all. So these are if you just divide it by the total number of counts of the reads, that also brings about the second like it brings about differences in all three genes across two conditions. Yeah, total count normalization produces the exact same result as no normalization at all, as the total read count for each sample is the same. In truth, there is no differences in expression of gene 1 and 2, and the relative count for gene 3 should be higher than found by no normalization or total count normalization. Correct normalization, therefore, makes the read counts of non-differentially expressed genes equivalent. So as you can see, if you normalize it if you normalize it correctly, the gene expression pattern of like 1 and 2 is same across both conditions, and it is not the case if you do not do any kind of normalization, right? So uh, equivalent, which also makes the relative expression of gene 3 correct. So, and this is the final figure. No normalization and the total count normalization fail to equilibrate the read counts of non-differentially expressed genes, resulting in each gene appearing differentially expressed. And the truly differentially expressed gene, which is the gene 3, is having in the wrong fold change, because it is technically it has increased, but in this plot you see uh, it's basically without normalization it's the same, but in incorrect normalization it slightly comes down, but the proportion of expression of gene 3 compared to gene 1 and 2 is higher uh, in, in the third correct normalization procedure. So correct normalization reveals no differences in expression for the non-differentially expressed genes and the correct fold change in gene 3. So the the idea behind this slide is basically like there can be many confounding factors to the expression or to the number of reads that are getting that are aligning to that particular gene. But you have to take that with a pinch of salt, and you have to consider all those confounding factors. What could be the confounding factor, maybe the sequencing depth, maybe the length of the gene, maybe something else. So these are the things that you need to keep in mind before doing differential expression analysis. Otherwise, it, you could get like wrong results. Right. Now, normalization can be classified into two categories. One is within sample and another is between sample. Within sample normalization helps to correct the expression level of each gene associated with the expression level of other genes in the same sample. So it's about normalizing by gene length, or normalizing by the total read count, or normalizing by the depth of coverage, whatever. So these are the kind of things that you normalize with for within sample normalization. So and there can be many methods for that. There the broadly studied methods for within sample and between sample normalization are RPKM and FPKM. We'll read about this in the coming slides. And however, the different gene lengths can lead to a bias in per gene variance for differential expression analysis of low abundance genes. In the literature, within sample normalization approaches for RNA-seq data have corrected the biases arising from library size, gene length, and GC content. So on one hand, you have within sample normalization. Why do you need to normalize within sample? Because the length of the genes are not equal for all the genes. So like depending on the length of the gene, that is proportional to the number of reads that are going to get aligned to the gene. And also the depth of coverage is also one such thing. And so the number of reads that are getting aligned to the particular gene is also dependent on the depth of coverage. The more the depth, the greater is the probability of more reads getting aligned to that particular gene. And within some and like within sample normalization can correct these biases for gene length and other stuff, right? So first metric and first couple of metrics is basically the RPKM and the FPKM. So RPKMs, it's read per kilobase per million reads mapped. Okay, so RPKM is that, and FPKM stands for fragments per kilobase of exon per million reads mapped. Okay, so what is RPKM? It is a normalization method. It is suitable for comparing gene expression levels within a single sample, rescaled to correct for both library size and gene length. So both RPKM and FPKM stands for fragments per kilobase of exon per million mapped fragments. It is analogous to RPKM, and it is used to specify specifically in paired in RNC experiments like Illumina, and the calculation of RPKM and FPKM for gene I is given by this formula. So you have Qi divided by Li by 1000 into addition of Qi by 10 to the power 6. So your Qi are the raw reads or the fragment counts. Your Li is the feature or gene or the transcript length. So basically you're normalizing by length as well. So length kilobase basis you're normalizing. So Li by 10 to the power 3. So you are considering those as kilobases. And uh, yeah, and the sigma qj corresponds to the total number of reads or fragments to that particular gene. And you are dividing it by 10 to the power 6 to get the number as per million, right? So both of them, RPKM and FPKM, is expressed in terms of per million. So for that per million, you are dividing it by 10 to the power 6. So if you like kind of rearrange these terms, this 10 to the power 6 and 3 add up. So 10 to the power 9 and goes to the top. So this becomes the formula, right? So here you are taking care of both the gene length and also the total number of reads that is getting mapped to a particular gene, right? Now another such metric is TPM. It's a simpler metric, but like anyway, so TPM was introduced in an attempt to facilitate comparison across samples. TPM stands for transcripts per million, and the sum of all TPM values is the same in all samples, such that a TPM value represents a relative expression level in principle that should be comparable between samples. So here also QI is your basically number of reads map, and Li is your length of the gene or the transcript length, and this sigma Qj by Lj corresponds to the sum of mapped reads to the transcript normalized by the transcript length. So Qj by Lj is basically you are adding up the total number of reads and you're normalizing it by the transcript length, which is Lj. And the TPM measure can be easily converted to FPKM, which is you basically divide FPKM by the sum of all the FPKM of all the reads that are there, and you multiply it by 10 to the power 6. But yeah, so with FPKM, you are considering the length of the gene or the length of the transcript here. Here also, you are considering the length of the transcript. It's just that this is you're basically measuring this in terms of kilobases and uh, per million. Here it's not the same. You're not measuring by kilobases, so that's why instead of 10 to the power 9 you come to 10 to the power 6, because that 10 to the power 3 you are not using. Okay, so this went for like TPM. We talked about RPKM and FPKM. There's one, there are other methods by which you can normalize as well, statistical methods. So, like one such type is basically count normalization method, which basically uh, is done using certain packages in R. So R package, this TX import is basically used to prepare gene level count data for RSEM output file. If you remember RSEM was the alignment tool that we used. And subsequently, normalized count data were derived from the DESeq2 package. The normalization approach used by DESeq2 is to form a virtual reference sample by taking the geometric mean of the counts of over all the samples of each gene. So if you have, say, three genes expressing, one sample and three genes is expressing say 25, 25, 25 transcripts. So how DSeq normalizes is basically takes the product of these three, 25, 25, 25, and it does to the power one third. So it's basically the geometric mean. So if you have five samples, so you will have x1, x2, x3, five genes, x1, x2, x3, x4, x5. You multiply all of them and you take to the power 1 by 5. So that is how you get the geometric mean. Yeah, so the normalization approach used by DSeq2 is to form a virtual reference sample. This is what the virtual reference sample is, by taking the geometric mean of the count of overall samples for a gene. Then DSeq2 normalizes each sample to this virtual reference to get one scaling factor per sample. So you get this amount, and then you get this value, and then you divide the expression or the counts or whatever that is by this particular value to normalize uh, the data set. Uh, yeah, another type of normalization is basically z-score normalization, when you are like you're trying to convert the data set to a normal distribution, and it's basically considered a centering and a variance stabilizing method, because you're converting that into a Gaussian distribution. Z-score on TPM level data is calculated using this formula. So basically, this is the Z-score formula only. Just you're taking log scale, right? So yeah, this is how it is calculated. So, and you remember the bases are two. Okay, so log of TPM plus 1 minus medium of log of TPM plus 1 by standard deviation of log of TPM plus 1. This plus 1 is added because the TPM might be 0, because when you are, like, say for example, a particular gene has not produced any transcripts that have been sequenced by the RNA-seq experiment, so uh, your counts data will be 0, and if you convert it to TPM, it will still remain 0 because your count is 0. Now, if you want to log transform it, if you cannot log transform 0, so that's why you add the 1 for that. Okay, yeah. So these are the major types of normalization methods that are used. You'll see, like you'll cover these kind of, uh, you'll see these kind of methods used to normalize data across literature, say mostly RPKM, FPKM, and TPM, majorly that those are used. There are other normalizing normalization methods as well. So you can normalize using anything depending on what exactly you want to know, what exactly your question is. But yeah, these are the standard normalization that are followed in RNA-seq data. You'll find those in. Now, hi Ismail. So there is no, like, you cannot say one is the most common normalization method. Depending, as I was saying, depending on what question you are trying to ask, you use the normalization method. So if your transcripts are in that level, so if your expression is very high across the board, so for example, so TPM and FPKM and these type of things are mostly used. So as you see, we normalize using per million. So there's a reason why we are doing per million, because your transcripts are very high in number. So normalizing by per million gives you a better scaling factor for the whole data set. Now, like if you want to see ekdam expressed, particularly how gene is getting differentially expressed between two conditions, FPKM and RPKM are methods that are most commonly used, because there you are taking care of the gene length as well. So depending on what kind of question you're trying to answer, that determines what exactly normalization method you would want. Now, if you want to just check for the same length gene, you just want to check what is the difference in expression. You don't need to normalize by the gene length, right? You can just take accounts per million and compare those, because they are of maybe the same length, or uh, they're situated right next to each other, so they are expressed in a similar manner. So these kind of things that you probably know from beforehand will determine what kind of normalization you'll do. But if you ask me what is the most common, I'll say RPKM of FPKM. You'll see those across literature. Okay. So now these normalization methods are there, but these are not without drawbacks. So uh, like, what are the drawbacks for these kind of methods? So poor performance when transcript distributions differ. So when transcript distributions are different between different samples, as in the distribution of the number of transcripts. So like, we generally follow basically a negative binomial distribution, where basically only a subset of the genes will be expressed much higher than the other, um, and the rest of the genes will have a similar kind of an expression. Now, this is kind of phenomenon that you'll often see in biological systems, and when you are doing RNA-seq. That's the whole idea. Like, 99% of the genes will behave in a similar manner. There will be some genes which are comparatively higher or lower. Sorry, but if the transcript distribution is different, so if you have set up the RNA-seq experiment in such a way, so say for example you have set up two RNA-seq experiments. In one, you are using a control set of samples where you are checking for expression in control, and then you have a disease set of samples where you are checking expression in the disease samples. Now, if you use different coverage metrics for both the samples, so you have done the sequencing for these two groups separately. So one will have a higher coverage, one will have a lower coverage. If that happens, I'm not saying it will happen, but if that happens, so the transcript distribution between the two types of samples uh, varies differently, varies majorly. So one might be like you'll have a higher set of ranges for the transcript levels. In one, you might have a lower set of levels depending on the coverage. Now, in those cases, what happens is if you directly use RPKM, FPKM, or TPM without looking into the sequencing coverage matrix, then what will happen is the normalization will not be all right, because since there is a distribution difference between the two the two set of samples, what you need to first do is normalize them to the same distribution. Then you use this kind of normalization techniques like RPK and FPK. If you directly use those, what will happen is you are not taking into account the coverage of the two set of different samples. So this can lead to misidentification of differentially expressed genes. So RPK and FPK, they do not perform well when the distributions between two set of samples are different, transcript distributions. So the idea is to get them to a similar type of distributions, similar type of scales. You scale or you do something else with that. Uh, basically you use central limit theorem and you calculate z-scores and convert both of them to a normal distribution. You can do that. Then you can use these RPK and FPK values. And it is also not recommended between sample comparisons. So the total number of RPKM, FPKM normalized counts for each sample is different, making it difficult to compare normalized counts for each gene between samples. And also, like this RPKM is not very suitable for differential expression analysis because they do not account for gene length. So here is a typo. They do not. Sorry, yeah, RPKM values are not suitable for differential expression analysis because they account for gene length. Okay, I think there is something wrong in this statement. Yeah, but please ignore this particular statement. Yeah. I'd want to say that TPM normalization has the advantage that the sum of all TPMs in each sample are the same. So if you do just transcripts per million, what you'll have is if you add all the transcripts for all the genes in one sample, it will add up to 1 million. So the total number of transcripts in all the samples are same. So that advantage has TPM normalization has that advantage that all the sum of all the TPMs in each sample are the same, making it easier to compare the proportion of fields that map to a gene in each sample. So as I was saying, depending on the type of question you are trying to answer, depending on what matrix can affect that question. So if you're looking for differential expression, a number of matrices can affect that. So you need to account for those through this normalization procedure. If your gene length uh, is affecting the number of feeds that are going to show up in your basically number of transcripts that are getting expressed, then you need to account for gene length and normalize using gene length. If basically your sequencing depth affects the number of transcripts that is getting generated, then also you need to account for those things. So basically, whatever question you're trying to answer and whatever confounding variables can affect that question, you need to account for all those things and normalize those accordingly. So yeah, so these are like standard normalization procedures. There can be other type of normalizations as well, where like depending on your requirement, you normalize it according to whatever metric you feel like, because that might answer the question you're asking. So yeah. Okay, so now we talked about like kind of same sample between sample, sorry, within sample normalization. Now there is also the concept of between sample normalization. Okay, so inter-sample normalization is essential for gene expression analysis. Here you account for what is known as sequencing depth. Sequencing depth, also known as library size, is the total read counts mapped to a given sample. There is no optimal level of sequencing depth as it depends on the complexity of the organism and the aim of the experiment. A deep sequencing which might improve the quantification and identification of transcripts, leading to novel isoform detection. However, it may also detect transcriptional noise and off-target transcripts as well. Sequencing different samples within a single experiment design may have different sequencing depths because the total number of representative RNA molecules in the CDN library can vary. So here comes the library bias and the sequencing bias. And composition bias refers to the types and the amounts of different RNAs in a sample. Composition bias can occur when some RNAs are more abundant in one group compared to others. So these are the different types of confounding factors you need to keep in mind. So like maybe just the composition in so for example, say you are comparing a particular control to a say a lung tissue RNA sequencing and a liver tissue RNA sequencing. Now both of them do not have the exact amount of transcripts as the same, right? So there are like the distribution also might differ because it's completely two different tissues, and like different types of genes are expressed in two different types of tissue. So there you need to keep in mind of the composition bias, where you have to account for the amount of different types and the amount of different RNAs in a sample. Right? This impact becomes more pronounced when a subset of genes within the RNA population is either exclusive to or characterized by high expression levels within a particular experimental condition. As I was saying, say in liver there will be a particular gene that is already highly expressed, and that is not a what to say like that is a characteristic of the tissue. That is not a disease condition or something else. That is not something you want to detect. That is already there. Then you need to account for that. Okay, like this particular tissue will have these genes which will have their expression high. These will be the genes which will have their expression low in a normal condition, right? So yeah, this becomes more problematic when the RNA population is either exclusive to, so for example a particular gene is only getting expressed in the liver tissue, not in the lung tissue, right? So RNA population is either exclusive to or characterized by a high expression level within a particular experimental condition. A reason might be due to contamination as well. So anything can be possible. Contamination is also something that you need to account for. When such a scenario occurs, a significant proportion of the sequencing resources is allocated to capturing reads from the specific genes, which decreases the reads for other genes, causing undersampling. If not explicitly accounted for, this can cause composition bias. Okay. Okay. So there can be different types of like methods to remove this intersample bias or between sample bias. So first, you do not do any normalization, which will become your negative control, and then you compare the normalized different type of normalization behavior against that negative control. So in case of no normalization, this negative control only has counts per million normalization and log transformation. CPM is a basic gene expression unit used to correct the sequencing depth variation. Now, TMM, which is known as trimmed mean of M values, is used for correcting the composition bias. So basically, one set of samples have that particular gene, one is expressing that particular gene, another set of samples is not. So this is what composition bias is, and this TMM is used for correcting the composition bias and is incorporated into the HR package, which is quite a common package used for RNA sequencing analysis. As a default to normalize data for differential gene expression. In the TMM algorithm, first a reference sample is chosen. A reference sample is one that is near to the average mean of all the samples. So you take the expression across all the samples and you take a mean. Whichever samples is closest to that mean, you take that as a reference sample. And then genes are selected to create a scaling factor. For this, the genes which are not outliers are selected. Outliers can be known by observing logfold changes. Logfold values are trimmed from top 30 and bottom 30, and mean of logs are trimmed from the top 5% and the bottom 5%. The genes which are overlapping from both trimmed logfold values and the mean of logs are used to calculate the scaling factor. Finally, our original read counts are divided by the scaling factor. How TMM is choosing a reference sample and creating scaling factors is a major difference with other techniques. This makes it robust technique to handle outliers. So this is one type of method where you detect those outliers, remove those outliers, and kind of bring down the logfold change to close to the average. So if something is standing out, it will stand out properly. Not like mm, you'll not have like 10,000 genes which are highly expressed. You are like bringing down the logfold change, and if actually there is a differentially expressed gene, it will stand out. Next is a variant of this trimmed mean of m values, TMM WSP, which is basically with singleton pairing. It's a variant of TMM to handle zero inflated data in the jar package. In TMM, if a gene has zero count in a pair of libraries while comparing for a reference sample, then it is ignored. But in this method, it is not ignored. Right? So there's a small caveat. Next, this is a quite a commonly used method for in-between sample normalization, which is known as the quantile normalization. So upper quantile normalization is determined by applying the 0.75 quantile to the gene counts from all runs, and it is applied to RNA sequencing data. The scaling factors are calculated from the 75th quantile of the library of each count. So basically you remove the outliers above 75 percentile, and then you calculate the scaling factor from the rest of the 75% quantile of the counts for each library. And the last type of normalization is the relative log expression normalization, which can be performed in the DE62 biconductor package, and it is very similar to TMM, in which there is a reference sample created by calculating row-wise geometric mean. So by in row-wise, you mean by like the geometric mean of a particular gene across all the samples. Then a scaling factor is calculated by using the median of the ratio for each sample in a log base. The median is another way to handle extreme values. Thus, the median is converted to a natural numbers from the log base to get the final scaling factor. And count values are normalized using these scaling factors. So these are the different types of techniques that are used for in between sample or intersample normalization. And within some sample normalization, we use methods like RPKM, FPKM, CPM, or TPM, whatever it is. Right? Okay. Okay. Now, this is another kind of, you can say, classify as intersample normalization, but this is not actually normalization per se. So what happens is, say for example, I don't think the plot here is very good. I'll show you something on the internet only. So that's effect. Let's see if you have images. Yeah, if you can see this image. So say for example, just like forget about TSNE, what is TSN and everything. Say for example, you are plot, you are imagining the samples in space with the coordinates being the gene expression profiles, right? For each gene. Now, what you do is you take a healthy set of samples and you take a disease set of samples and you do them sequencing separately, and then you form the RNA-seq dataset and you're trying to find differential expression or whatever analysis you're trying to do. Now, before doing the differential expression analysis or anything else, what you see is let's say for example the red ones are your control and the blue ones are your diseased samples, right? So what you see is your control samples and your disease samples are getting separated in space. They, like for control and disease, that might be possible, that might still be possible, but say for example you are comparing two different uh, sets of experiments but for the same tissue, two different experiments, and you're seeing that the separate experiments are clustering separately. So what it means is basically what we call as batch effect. So because of it being sequenced in a separate batch or a separate set of experiments, the overall value of the number of transcripts or gene expression is slightly higher or lower compared to the other set of batches. That doesn't mean that inherently it is higher. It's just the sequencing bias, right? So what we do is basically sorry, yeah, it's basically what is called as the batch effect removal. Okay, So batch effect across samples are easily overlooked but worth considering for cohort studies like immunotherapy. Batch effects are usually caused by unbalanced experimental design and confound the estimation of group differences. So basically, there's clear differences between these two groups when you like look into it from gene expression level, but biologically maybe there is not that much difference in the two set of groups. So that is where you can estimate that there is a batch effect there, and you need to remove it. So, batch effects are usually caused by unbalanced experimental design and confound the estimation of group differences. For example, samples processed at different facilities may have sequencing differences that are not due to actual biological differences in the samples themselves. To avoid confounding actual biological variation with the effects of the experimental design, we have a couple of packages called Lima and Combat. Lima is a very like widely used package. Uh, in RNA sequencing, you will see with different tutorials, GitHub workflows, and everything. Lima is a very widely used package. Yeah, so these are used to correct batch effects. So these are like standard uh, linear models or standard statistical models where we basically we model for this particular set of differences. So it uses a two-way ANOVA approach. This is analysis of variance. So if you don't know what ANOVA is, I suggest take a quick look. It's not that difficult. And Combat uses an empirical base approach, which is critical for small batches to avoid overcorrection. For large batches, both methods should be similar. The SVAR package, SVAR is another package which does batch correction, implements both combat and surrogate variable analysis for batch effect correction. Principal component analysis or unsupervised clustering before and after the batch effect removal is an excellent way to validate that the batch effect has been removed. So, as I was saying, imagining the set of samples in space, instead of doing that, what we do is the principal component analysis is basically uh, uh, it's taking what happens is your data is multi-dimensional, right? It's a very big data set. You have like thousands of features in the data set. What you want to do is you want to represent these 1,000 features with two features which can correspond to the variance of these 1,000 features. Like they can explain a certain amount of the variance of the 1,000 features by these two features. So principal component one versus principal component two. So principal component one explains almost 80% of the features and 80% of the variance. In principal component two, it kind of explains around 80% of the variance. Now, after batch effect removal, so what you see is if you look carefully here, there are three set of batches, one, two, and three. So the green dots have clustered together, the blue dots are together, the red dots are kind of together. There is a like a clear divide among the set of batches, and like it's not very good because if it is the same sample, there should not be batch effects, right? So when you remove this batch effects and plot this PC after batch effect removal, what you say is they kind of have come together. There is no systematic difference between the set of batches that have been already kind of batch effect have been removed from those set of batches of the experiment. Okay. Okay. So RNA sequencing does not provide measurements of absolute expression for each gene because in the RNA sequencing protocol, we'll use the key information telling us how much of total RNA was in each sample to begin with. Thus, it should come as no surprise that in order to compare absolute expression values between samples, we need to make some strong assumptions about our samples. For median ratio normalization, this is another type of normalization. This key assumption is as follows, that most genes are expressed at equal levels across all samples in our dataset. That is, each sample has a small number of genes that are expressed differentially from other samples. These genes may be the genes that are biologically interesting because like maybe those are the genes that are getting more expressed in disease condition and so on. Okay. But most genes are expressed at the same level, at same absolute level, as I was saying. With this key assumption, median ratio normalization uses all the samples in the dataset to compute a reference sample. This reference sample represents a baseline level expression for each gene. And this is basically a toy scenario where you have two samples and three genes. And this is your reference sample. So, reference sample as in, you know the relative expression between gene A, B, and C, and according to that, you are going to normalize it for both the set of samples. Right? For each sample, the most of its genes are expressed at the baseline level, as we have assumed. To make the samples comparable, we must identify one gene that is expressed at the baseline level. So this, if this is your reference, this is your reference, and you want to compare the set of samples with this particular reference sample, and like you want to say, compared to the reference sample, gene A or B is has higher expression or lower expression, something like that. So you must identify one gene that is expressed at the baseline level. If the gene deviates from the baseline level, then it means that there is library size effect that must be accounted for by scaling all of the read counts in the sample to ensure that the identified gene matches the reference sample. In this example, in sample 1, we identify gene C as being the gene that should match the reference sample's expression. For sample 2, we identify gene B to be matching to be basically a gene that should match the reference sample's expression. Just a second. Okay, so to normalize, we scale the read counts in each sample so that the identified genes should match the reference sample. Uh, Basically, what you do is you check, say for example, gene B, yeah, you are using it as a reference for sample 2. So gene B is kind of slightly lowered expression, has kind of slightly lower expression, higher expression compared to your reference. So you need to scale the rest of the genes in accordance to this particular comparison between gene B of your reference and the gene B in your sample. And similar in case of gene C in your first sample, then you need to scale it up a little bit to match the reference of gene C in your reference sample compared to sample 1. So this is how it would look like. So if you just say, for example, gene C, you are comparing gene C here, you have scaled it up a little bit, and with that you have scaled gene B and gene A up as well. And in the second case, in case of gene B has been scaled down a little bit, so gene C and gene A has also been scaled down. So there is a reference sample which you are using to compare two different other samples. So at first sight, it was looking कि gene C might have like kind of gene C in sample 1 might have less expression than gene C in sample 2. But if you kind of normalize this according to a reference sample, this is just read counts, right? This is nothing normalized anything at all. So if you normalize this according to a reference sample, then you see he's actually kind of the opposite. So in sample 1, gene C is kind of more highly expressed than gene C in sample 2, right? So this is basically like comparing two different set of samples using a third set of reference samples. Right? You compare anything and then you scale up and down depending on the level, expression level, and then you compare the both samples. Right? This is an interesting way to do it. Okay. Okay. So I think okay. Okay. So in quantile normalization, this we talked about here, right? So in quantile normalization, there are basically three steps available to do that. So first, you rank the genes by expression levels in each sample. You calculate the average of each genes and rank them across the sample, and then you replace the original value by the average value. It's kind of doing averaging out. Okay, so after you have done all this batch effect and correction and everything and whatever, there still can be some set of like QC still left to be done. Not like there needs to be like there are systematic differences which you need to like weed out to actually do the analysis. So depending on types of the systematic errors, you can identify them either by clustering. You do a PC, as I was saying, like see, these are like completely three separate types of samples that are here. So this most probably has batch effect. So most probably you need to look into the batch effect removal methods and correct this one. So clustering is one such example. Sample correlation, you can check for two different samples and how they are correlated, and if there is a higher set of correlation, then you need to know that there might be systematic differences between those set as well. You can do hierarchical clustering, saying ki which set of samples are closer together compared to the other set of samples. And also, as I was saying, principal component analysis. So these are different types of statistical techniques or visualization methods or analysis methods that you can use to kind of check for systematic differences in different samples and also within samples as well. Okay, now you have normalized, you have removed batch effect, you have done all the kind of quality control possible. Now you want to check if there is actually difference between like expression of one gene in two separate set of groups. The most easy way to do that is using a student's t-test. So this basically is the formula, which it's basically you are using the differences of means between two groups, and you are also like dividing it by the variability of the groups, which is the standard error. So along with the t value, you will get a p value associated with it. So if it is less than 0.05, which means there is less than 5% chance that uh, that interaction is insignificant, then you can like with statistical significance say that that particular gene is being differentially expressed compared to other set of genes. But this t-test, though simple, has a few problems. So first is like the number of replicates might be too low to uh, uh, undergo t-test to check check differences between two set of samples. It can have multiple testing issues, and it can have the major issue here is basically the distribution might not be normal. So for t-test to be implemented, the major assumption, the first and known, like the major assumption of a t-test is basically both set of distributions are normal. Now you can handle this, like even if you don't have a normal distribution, you can use z-scores and normalize them. That you can do, but still that is something you need to keep in mind whenever you are applying the t-test. Your set of data, both on both the groups, they must be normalized, or like the distribution must be normal, not normalization in terms of gene length, or I'm not saying that normalization, but normalization in terms of Gaussian normalization, like using central limit theorem to convert a particular distribution to a normal distribution, right? Z-scores basically. Okay. Okay. So as I was saying, okay, like there can be many issues. So yeah, uh, multiple testing issues. Basically, all of these like D, SIG2, HR, and Lima. So all of these are very famous packages for RNA sequencing data analysis. So these report Q values or some other type of false discovery rates or corrected P values. For SAMSIC basically based on resampling. For others, it's usually the Benjamin Hochberg corrected p-value. So what you'll see is along with the log fold change, you'll have a p-value which will tell you okay how significant that change is, and also you'll have a corrected p-value depending on the multiple testing, how many tests has been done. So you need to correct for that p-value as well. So yeah, these are the few issues with t-test. Now, as I was saying, basically if if you want to say compare two different groups, say you want to do t-test, all your conditions are getting satisfied. Now you want to compare two groups against each other. But what if you have to have several factors that you want to control for it? Say, for example, you have taken tumor samples at two different time points from 6 patients, cultured the samples, and treated them with two different anti-cancer drugs and a mock control treatment. So you have total. So you have taken six patients at, and you have taken tumor samples at two different time points and treated them with two different anti-cancer drugs. So and a mock control treatment. So total three. So three treatments, six samples, 6 patients, two samples. So 2 into 6 into 3, which is 36 samples. Now you want to assess the differential expression in response to one of the anti-cancer drugs, which is let's just call it drug X. You could just compare all drug X samples to all the control samples, but the inter-subject variability might be larger than the specific drug effect. Lemma DE6 HR, uh, which can work with factorial designs, but not uh, softwares like CuffDiff, right? So this is an example for given for Lemma. So Lemma stands for Linear Models for Microanalysis, but it was like brought in for microanalysis, but it can be used for RNA sequencing after applying this command to the count matrix. Essentially, the expression of each gene is modeled within a linear relation. So this is your model y equal to x beta plus epsilon, where x is your design matrix, beta is the parameters that you need to estimate using most probably it uses maximum likelihood estimation MLE, or there can be other estimation techniques as well. So this is a vector of your observed data. So this is like a one column matrix of your observed data. X is your design matrix, beta is your parameter, and epsilon is basically the covariates that you want to add. Now the covariates might be, like say for example, you want to describe the conditions, that is the treatment, patient time, etc., and you want to build the model. So y is basically your set of expression values or whatever you are trying to model. This is there will be a baseline. So here it's not baseline, is not given, you can add a baseline here. B is basically your treatment, B into treatment, C into time, D into patient, E into batch, and F, which is the error noise or error term or the noise term. So this y equal to A plus B into treatment, this is your just model, right? This is your original model. Now this time, patient, batch, and error term, these are your covariates that you want to control for while you are using the model, right? So you can use these kind of linear models. Lima uses this only, and like, there are host other set of applications for these types of linear models in biology. But yeah, so you can try it this way as well. Okay, now we'll look deeper into a particular what to say, particular software or a particular tool used for differential expression analysis. So we've seen the overview of what exactly are the caveats, what exactly do you need to keep in mind for different kind of things, and while comparing expression from RNA with different types of samples and everything, etc. Now, DSIC2 is one of the most popular, what to say, popular tools for differential expression analysis. The first step in the differential expression analysis workflow is fitting the raw counts to the NB model and performing statistical tests for differentially expressed genes. In this step, we essentially want to determine whether the mean expression levels of the different sample groups are significantly different. So this is one of your sample group. Basically, your red one is a sample group, blue one is another sample group. Now, the the group mean, which is given by this pink color with a black border on it. So the group mean for the blue ones is given here. The group mean for the red ones are given here. And This is your global mean. The yellow one is your global mean. So there is significant difference in terms of, like, if you compare group A mean to the global mean, and you compare group B mean to the global mean, there is a significant difference and significant deviation from the global mean for both the group means. So in this case, there is the significant difference. In this case, it's much closer and there is no significant difference. So in the first step, you want to essentially determine whether mean expression levels or different sample groups are significantly different or not. Right. Uh, Differential expression analysis with DESeq2 involves multiple steps as displayed in the flowchart below in blue. Briefly, DESeq2 will model the raw counts using normalization factors, which are size factors, to account for the differences in library depth. Then it will estimate gene-wise dispersions and shrink these estimates to generate more accurate estimates of dispersion to model the counts. Finally, DSIC2 will fit the negatively binomial model. As I was saying, negative binomial model is something kind of, you can call it a characteristic of these gene expression things, because, like, as the idea is correctly, 99% of your genes will have the similar kind of baseline expression. There will be a couple of genes, a very handful few genes, which will have more or less expression compared to the baseline. Okay. It will estimate gene-wise dispersions. We'll talk about what is dispersions and shrinking of estimates and everything. But yeah, so this is your overall workflow. So you start with read counts, normalize, you do clustering and everything. QC, you have done. Now you want to you'll perform you'll apply DESeq to your data. Sorry, apply DESeq to your data, and these are the 5 steps it follows. So at first, it estimates size factors. Next, it estimates gene-wise dispersions. Next, it fits the curve to gene-wise dispersion estimates. Then it shrinks gene-wise dispersion estimates, and at last, it fits a generalized linear model for each gene. Okay. So, and it also allows for the analysis of complex designs. You can explore interactions or the difference of differences by specifying it in the design formula. For example, if you want to explore the effect of sex on treatment effect, you could specify it in the design formula. So this is what you are specifying is basically are the covariates. So sex, age, treatment, and whatever extra you want to give. These are all your covariates that the model will take into account while performing the while building the linear model for each. Okay. Since the interaction term sex is to treatment is last in the formula, the results output from DESeq2 will output results for this term. Alternatively, as recommended in the tutorial or the weeknet, you can create a new factor in the metadata based on 2 interaction factors as shown below. So basically, you can use age and treat sex. So basically, this is combining treatment and sex. So you can do that, right? Okay. Okay. So these are your different steps. So first step is the estimation of size factors. The first step in the differential expression analysis is to estimate size factors, which is exactly what we did to normalize the raw counts. So basically how we normalize raw counts, it will estimate the size factors while performing the differential expression analysis. But like there is another command called estimate size factors in the EC2 which will estimate it beforehand. So basically this is a normalization step. We'll estimate like which gene is bigger, which has more transcripts, which has less transcripts, this kind of stuff. The size factors it will estimate. Okay. Now next comes the important part, which will estimate the gene-wise dispersion. Now first, we know what is dispersion. So dispersion is a measure of or spread of measure of spread or variability in the data. So how much spread the data set is, or how much variability or how much variance is it there in the data. Sorry. Yeah. So variance, standard deviation, interquartile range among other measures, can be used to measure dispersion. So dispersion is just measuring how spread out your data is, how spread out it is, or variate, how much variance it has. So you can use standard deviation technique, what to say, methods like standard deviation or interquartile range. Interquartile range is basically the difference of the 25th percentile with the 75th percentile of the data. So it gives you how much spread out that data is in a box plot, right? Yeah. However, DESeq2 uses a specific measure of dispersion, alpha, which is related to the mean, which is mu, and the variance of the data. So this is the model that is used. It is using variance equals to mu plus alpha mu square. Right? Your alpha is given by the expression is given by the alpha, variance is given by var, mu is the mean of the particular set of samples. For genes with moderate to high count values, the square root of dispersion will be equal to the coefficient of variation, which is var by mu. So 0.01 dispersion means 10% variation around the mean expected across biological replicates. Okay. So now you've calculated the dispersion, how much variance is there in your data, but why is it important? Like, what does this dispersion represent? The DESeq2 dispersion estimates are inversely related to the mean and directly related to the variance. Based on this relationship, dispersion is higher for small mean counts and lower for large mean counts. Dispersion estimates for genes with the same mean will differ only based on their variance. Therefore, dispersion estimates reflect the variance in gene expression for a given mean value. So what you are essentially doing is you're like, basically you're checking around the mean how much is your data getting like dispersed, how much is your spread. So if say for example in one sample you have taken the mean across all the 20,000, 25,000 genes you have got, and then what you're checking is like say for your mean is in the middle, so how much spread out your data is in both sides of the mean. That will tell you if there are particular data points which are there which have very high variance compared to the mean. Like if your mean is say like if, consider a normal distribution, say your mean is in zero. Now if it is more spread, so normally it will be like this. I'm just bad with this. So normally it is like this. If it is more spread, it will be like this, your distribution. So what it means is there are points, or there are particular genes in the data set which have much higher expression compared to the mean. So your data, if that happens, your data will be dispersed much more. So your dispersion is higher for small mean counts and lower for large mean counts. So if your mean is larger, which means almost all your genes are expressed at a higher level and your dispersion is not high. But if your mean is smaller, that means your dispersion might be very high because one is very, like, say, for example, one is, I'm just giving you numbers without units. Just like, say, for example, your mean is at 0, but you have one gene expressing at plus 100, one gene expressing at minus 100. But in this case, the dispersion is much more. Now, if you compare it to a mean of 50, that and one gene you have at 0 and another gene you have at 100, the dispersion is much lower. So the expression differences amongst the gene is much lower. So the dispersion estimates reflect the variance in gene expression for a given mean value. So that is what it is trying to do. Now, how does this dispersion relate to our model? To accurately model sequencing counts, we need to generate accurate estimates of within group variation between replicates of the same group, right? For each of the genes. With only a few replicates per group, estimation of variation for each gene are often unreliable due to large differences in dispersion for genes with similar means. To address this problem, DESeq2 shares information across genes to generate more accurate estimation of variation based on the mean expression level of the gene using a method called shrinkage. Like, DESeq2 assumes that the genes with similar expression have similar dispersion. This is also a very important assumption in the model. Now, how do you estimate the dispersion for each gene separately? To model this, based on expression level, which is the mean counts of replicates. The dispersion for each gene is estimated using maximum likelihood estimation. So, for example, in this model, so this is your like your covariate thing, but this basically a similar kind of a model to lemma it uses. Like it's also a linear model. So in this beta is your basically your set of parameters you want to estimate, and maximum likelihood estimation is one technique to estimate this set of parameters. Yeah, these two. Yeah, nah, to model the dispersion based on expression level, the dispersion for each gene is estimated using MLE. In other words, given the count values of replicates, the most likely estimate of dispersion is calculated. Now, if you see this curve displayed has a red line on the figure below. Just a second. Sorry, Ismail, I missed your question. No, reference samples are not exactly control samples, though you can, like, if you are designing the experiment that way, you can use control samples as reference samples. But reference samples are mostly a set of expression values that you already know. Say, for example, you're taking a liver tissue and you're doing RNA sequencing on it. But from previous studies from literature and everything, you know that like what are the different ratio of expression of particular genes that are there. So that can like your previous studies can those can act as a reference sample. Your control can also act as a reference sample if you know what actually the control is like, basically how the expressions are same or different across different genes for the particular control sample. You can use your control sample as your reference sample, but generally reference samples you'll use like already known like tissues or samples that you already know and how the gene expression looks like and how much differences are there. Not exactly the like by gene expression looking like, I do not mean ki the gene expression like values. What I mean is the ratio of gene expressions of particular genes, right? So if you already know that fact, yeah, you can use control samples as reference samples. Yeah. Okay. Okay, so the curve displayed as a red line in the figure below, which plots the estimate for the expected dispersion value for genes of a given expression strength. Each black dot is a gene with an associated mean expression level and a maximum likelihood estimate of the dispersion. So basically, this is your normalized counts, and this is your dispersion, how much dispersed it is. So these blue dots that you see above, so these are like having medium mean, but they have very high dispersion counts. So this red line is basically the most, what to say, the best estimate of the dispersion for the basically for the whole set of genes. So these black dots are all your genes. So what is this line is basically the best fitting line that is the like that is explaining the dispersion versus the mean normalized counts for all these genes. So these are your data points, and this is a fitted line, regression line. Okay, so this is not a linear regression, but anyway, yeah. So yeah, this is so now comes to the fourth and the final step, which is the no, I don't think it's the final step. Oh yeah, this is the final step. Yeah. So yeah, the fourth and the final step, which is basically shrinking gene-wise dispersion estimates towards the values predicted by the curve. Uh, basically, you are trying to shrink the gene-wise dispersion estimates towards the expected dispersion value. So you have a model and you have a set of expected values, dispersion values from the data that you have generated. Now you want to shrink your original data to original data for gene-wise dispersion estimates towards the expected values. So you have a set of expected values and you have a set of values from the calculated from the data set. What you want to do is you want to shrink those particular extra particular values that you calculated from your data set towards the expected line or the expected curve. The curve allows for accurate identification of differentially expressed genes when sample sizes are small, and the strength of shrinkage for each gene depends on how close gene dispersions are from the curve and the sample size. The more the sample, the less the shrinkage. This shrinkage method is particularly important to reduce false positives in the differential expression analysis. So this is a little bit intuitive. You need to think about it. So if you have what you exactly are you doing with this shrinkage? What you are doing is basically bringing out down the log fold values to a more expected range than a very random high range. So what you're doing is you're trying to bring this towards the same set of expected values, so you do not have very high log fold change or like very high changes in uh, very high differentially expressed genes technically in terms of that. So how you're doing is basically you're trying to get those towards the estimated curve, the gene points towards the estimated curve. And what it does is, if you're reducing the amount of log fold change, what you're reducing is the probability of getting false positives in differential expression analysis. Right. So genes with low dispersion estimates are shrunken towards this curve, and the more accurate, higher shrunken values are output for fitting of the model and differential expression testing. Dispersion estimates that are slightly above the curve are also shrunk towards the curve for better dispersion estimation. However, genes with extremely high values of dispersion are not. So there needs to be a cutoff. Like how much higher value will you not bring down? Or how much till what value will you try to shrink it, till above what value you will not try to shrink it. So that kind of cutoff you need to have, because if you're shrinking a very high log fold change towards your expected curve fit, then what happens is that you're like that will be that will be a true negative, right? So it's actually a differentially expressed change, but due to shrinkage, you are bringing it back down to its down to an expected value. So those the kind of things you don't want to do, because you'll lose out information. So you'll have a cutoff, and below which you'll try to shrink the values so that your log fold change looks cleaner. So the the differentially expressed genes look cleaner, right? So yeah, dispersion estimates that are slightly above the curve are also shrunk towards the curve for better dispersion estimates. However, genes with extremely high dispersion values are not. This is due to the likelihood that the gene does not follow modeling assumptions and has higher variability than others for biological or technical reasons. So, like for technical reasons, variability you have already weeded out with batch effect removal, with composition bias removal, with different kind of bias removal you have already removed out. Even after that, if a particular gene is having very high dispersion, what it means is basically that might be the gene that is very highly expressed or very high has very high log fold change. So we define differential expression in terms of log fold change, basically, which means how much it has changed compared to before. Like that is like it gives you a value which is basically 2 times, 3 times, 5 times, whatever. So uh, yeah, what it means is basically if you have a very high dispersion value, there is a good amount of probability that that particular high dispersion is not due to any other reason but due to biological reasons, right? That is not something that you want to lose, so that's why you do not bring that down. Shrinking the values towards the curve could result in false positives, so these values are not shrunken. These genes are shown surrounded by blue circles below. So these are the high dispersion ones, right? These ones. The other ones you see are shrunk towards. So just below the line, just above the line, they're shrunk. But the ones that have high dispersion values, very high, they are not actually. And the three legends here is basically this is your fitted value, which is your prior mean, and MLE and MAP are two different estimation techniques. So MLE stands for maximum likelihood estimation, and MAP is uh, a priori estimation technique. It's a Bayesian technique. Okay. So this is a good plot to examine and ensure that your data is a good fit for the DEC2 model. You expect your data to generally scatter around the curve with dispersion decreasing with increasing mean expression. So like with increase in mean expression, your dispersion should decrease. So anyway, they should have a negative correlation, right? So that kind of trend should be followed. Okay, if you see a cloud or different cloud or different shapes, then you might want to explore your data more to see if you have contamination, which might be mitochondrial or other kind of PCR contamination and other stuff, or if you have outlier samples. Note that how much is shrinkage you get across the whole range of means. In this is the plot function for this plot for any experiment with low degrees of freedom. Examples of worrisome plots are given below. So these are kind of plots which are worrisome because you have it all around the kind of it's basically forming a cloud type of situation um, around your best fit curve, and if with increasing mean normal counts, the dispersion is not coming down. This still is possible, but see, you have another set of data points here which are like not good actually. Okay. So these kind of plots are actually good. So you can see a clear negative correlation here. And like dispersion actually comes down with increase of mean normalized count. Okay, yeah, that's all for the revision part. Now we'll go for the assignment problems, uh, previous year assignment problems. Okay, just yeah, I'll give you a couple of minutes to do this, and you can write the answer in the chat. We'll discuss this after that. see. You have any answers yet? One. Okay. We can give another minute. Yeah, just 1 second. Okay, let's try it. So first, you're asked key in what is the read counts in gene C of replicate 2 after TPM conversion. One is not the answer because like this is the counts. You need to convert it to TPM, and yeah, this is how you do it. So 3 steps in TPM conversion. First is divide by gene length. This will provide reads per kilobase, and you have to divide it by 10 to the power 3 as well for kilo. So it's given in kb also, so you can directly divide it, and then you estimate the scale factor and you divide them by a million, and then you divide the rpk values with the scale factor. So basically the scale factor will be the total, what to say, first you need to divide it uh, by the gene length. So you divide the replicate to all the genes. So this is 1 kb, so this is remains 17. If you divide it by this, by 2 kb, it becomes 5.5, and this is zero point 0.2 divided by 5 if you do 1 divided by 5. So the scale factors will be addition of all this divided by the total, divided by 10 plus 6, which is per million. So total divided by 10 to the power 6, so it becomes 22.7 into 10 to the power minus 6. Now you multiply. This is not 1 actually, this is zero point 0.2, so you have divided by 5. So you multiply 0.2 by the scaling factor, and this is what it becomes. Like the answer is 8810.57. Mm, just a second. Yeah, zero point 0.2 divided by your scaling factor. That is the value of TPA of this gene C after TPM conversion. So, like, sorry if I confused you. So, first thing you need to divide by gene length. Then you need to calculate the scaling factor. How do you calculate the scaling factor? You add all the um, gene expression values, which is normalized by gene length, and you take the million thing here. So, 10 to the power 6. Divide them by a million, so which becomes RPKM. So per million you do that, and then you do the TPM calculation, which is just dividing the expression value, which is normalized by your gene length. Divide that by your scaling factor, you get the answer. Simple. Okay, moving on. Sorry. Okay, it's quite simple. You just need to take the geometric mean. The geometric mean is like multiplication of all these, like these four numbers, 1000 to 17 to 156 to 190, and take whole to the power one fourth. That's how geometric mean works, right? So yeah, you multiply these and take to the power one fourth. This will be your answer. I did not check if somebody has given. Yeah, it's correct. Thank you. Yeah, you just need to multiply and take to the power one fourth. That's all. Okay, moving on. Okay. Yeah, that's correct. Negative binomial is the way. So that is the major type of kind of distributions that you'll see across in different types of tools that they use. They assume that it's a negative binomial distribution. So quickly, I'll show you what a negative binomial distribution looks like. Yeah. Oh, this picture is too small. Just a second. Yeah, this is how it is looking like. I don't have a better picture for this. So you have a lot, like what to say. You have on the smaller end, you have no. I think I'm doing it wrong. Yeah, this is a better. This is the PDF, right? Yeah. So this is a random variable and this is a PDF. So on the both ends, you have like very small amount of what to say, small number of data points. So at the towards the tail of the distributions, you have very small number of data points, which means you have very small number of genes that are very highly expressed, and you also have a very small number of genes that are very low expression. Maximum you have is around the mean. And by dispersion, so how does the dispersion vary? So this has low dispersion, this has medium dispersion, and this has the most dispersion. Right. So this is what actually dispersion means in terms of like plotting the distribution. So and the idea is that on the lower end you have very few data points as in genes, and also at the very higher end you have very few genes. So maximum are like around the average. That is what the idea means. Yeah. Okay. This. Okay. See. Yeah. Yeah. The answer is TMM, which basically sorry. Yeah. Yeah, the answer is TMM, which is basically trimmed mean of M values. So we discussed it here. Let's go back quickly. Yeah. So this is the TMM. Okay. Mm, Okay. So first you need to for the SIG2 you need to find the pseudo reference counts, which is basically the geometric mean of all three. So you do that geometric mean. After dividing the counts of sample A with pseudo reference counts, we can find out the size factor for sample A. So you just need to divide 25 divided by your pseudo reference counts, which gives you the size factor. For all three, the median value of all gene counts in sample A will be 1.81. This is the calculated size factor for sample A. So for calculation of size factor, first you need to find the pseudo reference counts. You need to divide all the gene expression values, count values by the pseudo reference counts uh, for that particular gene, and then you take the median value of that. So in this case, it's 1.181, which is the size factor. The calculations, like the questions might seem a little bit, what to say, difficult, but these are actually pretty simple. Just you need to do some small calculations. That's all. It's actually, yeah, uh, simple. So I'll just quickly show you the truth table. Yeah, so this is your basically truth table. So if it is rejected, if your null hypothesis is rejected and it turns out to be true, it's a false positive. It is the type 1 error, which is the false positive. And let me get this out. Yeah, and yeah, yeah. This is a these two are correct decisions. So this is basically you're accepting it and it's true, it's a correct decision. This you're rejecting it and it's false and it's a correct decision. Both of these are correct decisions. Type 1 error is basically uh, you are it's basically false but you are saying it to be true, and type 2 error is basically you are saying it to be false but it's actually true. And it's actually yeah, you're saying it to be false but it's actually true. So false positive and false negative. False positive is type 1 and false negative is type 2. Yeah. Out. Yeah. So total number of differentially expressed gene is given as 500, and total number of genes used is given as 20,000, and your false discovery rate is set to 0.05. It's basically you do not need the total number of genes anywhere. So it's basically the false discovery rate is calculated on the differentially expressed genes. So it's basically 0.05 of this 500, which is 25. Yeah, that's correct. Okay, I've put the answer here only, but yeah, this is how the coverage ratio is calculated. So calculate the coverage in your disease sample by total divided by the total number of feeds. Do the same for the healthy sample. So your coverage here was 40 and your number of feeds were 2000. So 40 divided by 2000 divided by 80 divided by 4000. It's like 1:1. Okay. So it's quite simple. Ratio of diseased and healthy. So you take the ratio of like 2000 is to 40 and then you take 4000 is to 80. It's the same. Okay. Yeah. So you have basically you have uh, if you add this up, total count in sample B 9, 6, 5, 25, and 20, you get 65. Then then the count of gene B in sample B will be 6 divided by 65 and into 10 to the power 6. So yeah, that's correct. Okay. Yeah. It's heavy. Do you have any answers? Okay. Yeah. So the question is, what will be the value of gene C in replicate 1? So this value, gene C in replicate 1 after RPKM normalization. So total count in replicant 1 is 33, dividing the raw counts of gene C in replicate 1 by the total count. So basically 15 divided by 33, this gives you 0.455. And then you convert it to RPKM. Sorry, 1 second. Yeah. Then you convert it to RPKM. So 0.455 into 10 to the power 6 and 5 kb is your gene length. Sorry, gene length. And so you divide it by that. So it's around 91,000. I did not see the answer. No, it's actually 91,000. Simple. Like you take the total of this, then you divide the count of gene C by the total, which you get this value, and then you convert it to million and divide it by the gene length for RPK. Yeah, that's all from my side for today. Yeah, if you have any questions, you may ask or okay. I guess there are no questions, so I'll close this session. Thank you for joining. We'll meet you next week same time. Thank you.